så lang tid du ønsker, forhåbentlig ikke mere end en halv time tid. Og så smider vi alt ud, og så til sidst kommer så ind og får en karakter. Ja.
Og ud fra at alle så kan jeg til dansk, så tænker jeg bare på dansk. Godt, så har vi jo det er et speciale forslag om en effektiv distribueret algoritme til at lave geneflugtring. Jeg vil starte med i dag at introducere jer til området omkring metagenomics, som jeg har en fornemmelse af, for det er jo lidt ved siden af computer science. Så vil vi snakke om, hvorfor vi har brug for nye distribuerede løsninger til nogle problemer, der er inden for genetik. Derefter vil jeg gå videre til at præsentere det, jeg har lavet, som er den her algoritme, PECA. Og så vil jeg snakke lidt om, hvor godt den performer sammenligner med eksisterende tools. Og sidst vil jeg snakke lidt om, hvordan man kan bruge det, jeg har fundet ud af i fremtiden. Så lad os starte med introduktion til genetik. Alt det her er altså meget overfladisk standard, men bare lige for at give en fornemmelse af de problemer, der er, og så videre. Vi går nok på ingen måde dybden i genetik. Men bioinformatik, genetik, handler meget omkring, at man bruger de her sequencing-maskiner. Hvor det er, at man tager en prøve fra en organisme, og så lagde, og så kommer ud på den anden side kommer en liste af de gener, som er i genomet for den her organisme. Der er lavet rigtig meget god videnskab i dem. Og så er nogle ting, hvad nu hvis i stedet for at tage en organisme, tager en prøve med andre organismer, som f.eks. en fællesprøve fra vores indhold, som det er den, jeg har lavet. Der får man også en liste af gener ud. Så det fungerer umiddelbart fint, men problemet er, vi ved ikke, hvad for nogle af de her gener, som passer sammen og kommer på hvad for nogle bakterier. Så det første, man prøvede at gøre, det var, at hvis vi har bakterier, vi allerede ved findes, kan vi referere, kan vi sammenligne de her gener med dem. Og der kan man finde nogle enkelte. But a lot of them we were not able to find. So scientists have to come up with a new way to figure this out. So they came up with this metagenomic pipeline, where they start by running the sequencing machines on many different samples. Then they use gene clustering to identify the same gene across all the samples. And then that's look at the abundance or frequency of genes in each sample to construct the genomes, because we expect that two genes from the same bacteria, they will go up and down in the abundance together across both the samples. I will focus on the second part here, so the two remaining parts will not be talked about further. To understand how gene clustering works, we must first understand what a gene is. So this is very simplified, but essentially it's just it takes a string, and contains these four letters A, C, D, T. So that seems pretty simple for computer scientists, but when we compare these two, we must be able to take mutations into account. So essentially, the same gene for two different individuals of the same species will be slightly different. So we need to be robust to that and still consider these genes the same. The way you compare the gene is that you start with doing this alignment. So you take two genes, you put them into an alignment algorithm, which we will just treat as a black box for now. The important thing is that the algorithm inserts these small gaps here. So it's trying to optimize the positions where the characters are the same or identical. When you have such an alignment, you start by counting all the positions where the characters are identical. You then take length of the gene, all the entire line. You divide those up and get this fraction 60, in this case 62%. And that's called gene identity. Note that identity here is a fraction, which is a little uncommon for computer scientists. The state of the art, or the de facto standard, is that if the gene identity is above 95%, we consider these two genes to be the same gene. When clustering genes, we have this relationship between some genes are identical and some are not, depending on this 95% threshold. That's a little uncommon compared to other kinds of clustering. On top of that, we also have to deal with that the sequencing is not perfect. So, for example, assume that all these different DNA strings are the same gene originally, but different ones through the sequencing machine, colored slightly differently, some could define an entire gene, and so on. So we need a way to do clustering that can handle both these characteristics. That means that we cannot use the default ones like k-means clustering and so on. We have to do something else. And the way this is done in bioinformatics and in existing tools right now is that it is censor-based or representative-based. So you find one gene and you say this is the representative of the cluster, and then you take then you can put all other genes that are at least 95% identical to that one into the same cluster. This has the peculiar thing that not all members of the clusters are necessarily identical. So we might have a situation where this one aligns very well with the center, and this one aligns very well with the center as well. But together they only overlap a little bit and are aligned pretty good. So they will not be considered identical. So again, this is a little bit different from normal clustering. Great. Now I mentioned that there are already tools that deals with this kind of stuff. So why do we use something new? And essentially, it's because we need to distribute the computations onto more machines. Right now, computation can take a few weeks to complete, which is far too long. And you might think that, hey, we can just wait 10 years and computers are 1,000 times faster than a problem. But in the case of bioinformatics, it is. Because even though computers double their performance every 18 months, the performance of these sequencing machines doubles every 5 months. So the problems that we'll be working on will increase the size much faster than the computing power. So the only way to keep up with that is to use more machines. And this is not done until now because essentially distributing algorithms is pretty difficult. You kind of use a simple brute force algorithm as a hand solve. It gets the job done, it's simple, it's pretty easy to use, you don't have to think much about it, and if you only have a small job, that's perfectly fine. If you need to get some more job done, you need something like a chainsaw or an efficient algorithm. You have to learn how to use it, you have to be careful you don't do any damage, but it's much more efficient if you do that. And having efficient algorithms distributed on many machines, often because you have to think about synchronization, load balancing, fault tolerance, and so on, so you often feel like that you are jumping the chainsaw to keep all these things in sync. Luckily, there have been some progress to handle this. And the way this is handled is that, as in all other areas of computer science, we try to increase the level of abstraction. Just as we have seen with languages that have been more and more accurate over the years, the same has been true for distribution frameworks. But until recently, that's like 10 years ago, the most accurate was MPI, which was only on the level of like C language, so not that high level. But along with the rise of cloud computing came frameworks like Apache Spark, which is the one I was using, and Google Cloud Dataflow, and Hadoop, MapReduce, all this kind of stuff that makes it easy to write massively distributed algorithms. So now we have a different problem. We know that there's a need to distribute the algorithms. So now we'll switch over to the word that I'm contributing a little bit. And the Thesis primarily this PECA application. So the idea behind PECA is that it's difficult to do some efficient indexing directly on the genes because we don't know how the alignment algorithm will, or which characters it will compare together. So instead of doing something directly on the gene, we will find a good proxy for the gene identity that can indicate whether two genes will be considered the same. We then combine that with an efficient way of calculating these proxies in a distributed manner, so we can construct a candidate set of all the pairs of genes that we think might be the same, or considered the same. Once we have that, we can go on to do the actual clustering, which I'll get back to in more details in a minute. But for now, I will explain the proxy and this efficient proxy calculation. The essentially a k is just a sequence of k characters. Computer scientists would usually call them n-grams. And the k-bit profile is a long vector where each position in the vector counts the occurrences of each k in the gene. So for example, over here, you see it's 2, or in the AA column for G1, because we have AA here and AA here. And then you fill out the entire vector. It turns out that the correlation between this k-bit profile is a pretty good indicator of the geneticity. I have found in my thesis that cosine similarity and PECA correlation works better as a predictor than the metrics that are commonly used in the bioinformatic software. An example of this is here. So here we have two charts showing essentially the same thing, but different data sets. All the blue dots are half genes. And they, on the y-axis, there is the cosine similarity of their k-bit profiles. And on the x-axis, we have the gene ancestry. They have been cut off at 30 and 60%. Because there's only too many pairs for the software to plug everything. So you see a k equals 1, that's only counting the number of different characters. This does not much knowledge, but as we increase k, we'll see that all the low ones we don't want to find, they drop quickly. But the high ones above 95% here retain a high value for approximate. And as we increase k even further, this amplifier, so we're able to easily have a cutoff value around here-ish and get all the ones we want, but only a few of the ones that we don't want. And that's the basis for creating this candidate set. So now we only need a way to find these values efficiently. And the way I've done that is that I have that we've worked, I've generalized a disco algorithm on an algorithm called Disco, which was developed at Swift a few years ago. And the essential thing is that it works on any kind of correlation metric C that can be written as a sum of some added function. And the function is a added function. It takes two coordinates at the same position from different vectors. So for example, for cosine similarity, which has this function, the added function will be this function. The great thing about cosine similarity is that we can normalize the vectors without changing the value. So we can normalize the length to 1, which means that it reduces to only the product of two coordinates. The idea behind Disco is that instead of comparing each pair of vectors, we'll look at each cross column, one position across all vectors in one go. This is especially efficient if we have only a few non-zero values, so if you have a high sparsity in the vectors. And the way that we do it is that we start by, in parallel, going through all the vectors across all machines. And then in each of these columns, or cross columns, in each column, we look at all the pairs, values, and they identify all the label for the vectors. We calculate this adding function and multiply it with a tree grammar line, which I'll come back to. Then here down here, immediately random variable. It has the expected value of alpha, of A, and is keyed by the vector pair label. The reason why we do this randomization is that in this one we make fewer but larger values instead of reading a lot of small values. That means that the framework will have to deal with fewer elements that they just solve and sum up, which makes it much more efficient. In the last one here, we're going to sum it up with the framework, sum the values of the elements by the vector label. And the last thing we need to do is only to divide by lambda, because the expected value of all these is the added function. Then we'll get a good approximation of the correlation. The great thing about the student parameter lambda is that as we increase that, the runtime will increase linearly, but the error bound on this approximation will decrease exponentially. So we have a great trade-off between runtime and error bounds. Great. So now we have a function. We have an efficient way of computing that. So I can put it together into the, or align all those and keep only the ones that are identical, and we'll put that into an identity graph. That graph has the genes as nodes, and they're connected if they are deemed the same according to this alignment. So they'll be edges. Lastly, we use that graph to do clustering. And because we know all the neighbors and all the ones that are identical, the clustering is essentially just figuring out which genes will be the center genes. And then we can just assign the neighbors as members in the cluster. The way I select centers is in this algorithm. Essentially, the first thing we do is that we assign the IQ. That is just a quality measure for all genes of anything. Don't worry about the formulation, that's more than the thesis if you're interested. But the idea is that all genes get this value that indicates how good will this gene be if that is selected as a center. Then we say all the genes that has the best quality among all their neighbors, we'll make that centers. We'll remove them and all the neighbors because they can become members. So we will remove them from the graph, and we will repeat over and over until the graph is entered. So that's a pretty simple brute force approach to finding centers, or brute force greedy approach. So how does this work in practice? In this part, I will present some charts where often it's the same chart on both sides, the same data. On the left, you have a linear y-axis, which is good for seeing the relation between set things. And on the right, you have the logarithmic, so you can get into the details, especially the lower levels. The first one we'll look at is how well it compares with the existing tools. So the purple one here and the blue one, those are the existing tools, the U-Cross and CDHit, running on a single core because it cannot be multi-thread. And CDHit on the blue one runs on one machine with 32 cores. The red and green one are PECA, running on 4 and 32 machines respectively. We'll see that first of all we have this for small data sets too much overhead, but then on small data sets you don't need to distribute anyway, so that's not a big problem. Once we get above a certain size, we perform 1.7 times faster than CDHit and 40 times faster than U-Cross. 1.7 might not sound as that much when we use 4 times as many machines, but first of all, we don't expect CDHit to distribute as well as this algorithm does. And secondly, this is a math thesis. The CDHit is taking your software and optimize and run cheat code and all that stuff. So this is actually pretty good. And we can achieve even better performance by adding more servers, as the green line shows. So let's dig a little more into the runtime. So this shows the scalability, that is, how much longer does it take when we add more data. The blue is the overall line, so you start increasing a lot. The most important thing here is the green line. That, you see, it quickly ends up becoming the dominant part and scales pretty badly. And that's the alignment time, that is the time we spend on filtering this candidate set. If we somehow can get rid of this, we will already now, without a lot of optimization, be more than 4 times faster than CDHit, using only 4 machines. So this might be a good idea to look into how we can reduce that. I've done some work on this. And the idea behind it is that in the current solution, we align before we do the clustering. This is pretty nice because we can then select centers directly on the gene identity. The problem is that we'll also align all these member pairs with each other, a lot of them. But we only really need to know the identity between the center gene and each of the members. So the idea behind our proposed optimization is that we align during the clustering cycle, postpone the alignment. And if we can select centers efficiently based on the proxy value only, then we can know the centers and we can align only the center member pairs to check whether they actually belong in the same cluster. So I implemented this using practically the same algorithm as before, and it turns out this worked pretty bad. The two left here is the normal one, runtime, which is then takes most of the time. And the green over here is the time spent clustering. So suddenly, the performance suffers a lot. I'm looking to why this is. And the first thing is how much longer does it take to do the alignment in each draft? And it turns out it actually doesn't take that much longer. A little bit more, but not that much longer to do the alignment while we're clustering. The big problem is that we do a whole lot more rounds. So instead of doing like 4 or 5 rounds, we do 100 rounds. Which means that the algorithm for selecting these centers is very inefficient. I have to have a lot of repetitions to complete. So the conclusion is that if we can find a efficient algorithm that doesn't need as many iterations, we will be able to improve the efficiency a lot because the round time is not increasing a lot. The last chart that I'll show you is the parallelizability. That is how much faster does the algorithm run when we add more resources. You see that in general, especially on lower servers, we improve the performance rate. It kind of flattens out on higher numbers. But if you look into more detail over here, you can see that most levels they drop down and have flattened some overhead here. But that's so low that's not really a big problem. What is the problem though is the blue line or the Turkish line, which is the time spent on clustering. And that increases a lot when it increases on the service. This is the counterintuitive that we do the same amount of work with more machines, but it takes longer. So I tried to do some more digging down into that, looking at numbers, and it finally led me to go into the source code of the binary graphics that I use to do these graph computations. And it turns out that there is a bug there that creates a big index table that is squared in the number of cores that we're running on. So we get much more work just with this overhead index table. I've reported that, so hopefully it will fix in the future. The library is still in alpha, so that's definitely room for improvement. Great. In the last minutes here, I will talk a little bit about how the knowledge I have found can be used in the future. And the first thing is that we can improve this algorithm even further. So the most important thing is if we can find an efficient way to solve this proxy-based center selection problem and reduce the number of rounds we need to find centers. If that can be done, we are on the way to being unambiguously bigger than the existing tools, even on comparable hardware. The next thing is some problems in Spark. I mentioned the Spark on FX. I've also had severe problems with garbage collection, so bad that I was not able to run the full data set. Spark is working on this, and there's an update there this fall that should hopefully solve this problem. If not, we won't have to deal with garbage collection tuning, which is a bit of a pain. This can also be solved by using different frameworks that are similar to Spark, but it doesn't have this problem. If these are solved, we can start into improving the implementation, stuff like switching to a better serialization than Java's default, and optimizing the way data is represented around the network. Will also increase the runtime quite significantly once the other two are solved. Another thing we can do is apply the knowledge I found to solve other problems. The proxies I found for gene analysis can be used in the future algorithms and bioinformatics. The generalization I found with this algorithm can be used to plagiarism detection, finding bits of text copied around from the internet. And subject mining, where we want to find words that describe a subject based on a whole or large collection of online documents. And lastly, we can use this proxy-based center selection in other areas where we have this identical, non-identical relationship between entities, such as human fingerprint clustering. In summary, I have created PECA, which is an algorithm that performs competitively with existing tools. I've also proved that there are great opportunities by moving to the cloud and using these model frameworks, even though you're not using highly optimized C code. I've also, in the way of doing this, created this, found this new way of proxies for data analysis, generalized disco algorithm, and defined a new algorithm problem of proxy-based center selection, which is the thing of most computer science academic interest. Thank you all for coming here. That
thank you for your presentation. The thesis. We will ask some questions now. I guess it's in the tradition to allow the external attendant to go first.
Yeah, sure. If we sort of begin at like a very high level, you said that both in the thesis you state, and also on one of the last slides here, that this work demonstrates that moving to the cloud has benefits. And that just has me wondering, so why is this the cloud, other than, a traditional distributed approach to solving large computational problems, and how is the cloud special in this?
So the primary benefit of the cloud compared to on-site data clusters that we use in such a world is that you're essentially renting it on a hourly or minute basis. So let's say, for example, I've done this, I need a lot of computing power when I run a test. When I did my development research, I didn't need it. So when I need the power, I get a lot of power by renting it. And when I don't need it anymore, I release it, and I'm not paying for it. If I work on a university, and especially if we have in the academic year, some parts of the academic year people are on holiday, so there's low demand for resources. Other part of the year might be leading up to call for papers, all the places where you need to do a lot of computations. So in these areas, you will either have to wait a long time to get.
Yeah, so I understand that it's just that the bulk of your work is on the technical level, on how to discover on the algorithmic level, on the technical level, how to solve the algorithmic problem of clustering things, right? The cloud doesn't seem to come into that. I understand that it helps you development-wise and financially, but the algorithm itself does not seem to fit into the cloud.
So you will be able to run this on a compute cluster as well, having this framework run. But the advantage is that if you want to move to these platforms as a service, you have on the cloud where you can put it up there and they check out auto-scaling for you, so you don't have to predict how much resources you will need. They will take care of fault tolerance. If you're suddenly running on 10,000 machines or 1,000 machines, one of them will probably die at some point, so you need to be able to handle that. And in order to benefit from all that, you cannot use the existing C-based tools. You need to move into these cloud framework like MapReduce or Spark or Google Cloud Dataflow because that is the API exposed. You cannot get access to that flexibility and ease of use if you do not use these new protocols.
Right, but if I can challenge that a little bit, I can just keep talking. So you state in the beginning, both in your lecture and in the report, that up until recently we had only MPI as the sort of main parallelisation library. I don't think it's entirely true. Parallelisation is an old thing, right? There were libraries before MPI and there were functional tools, but true, there was nothing as popular as MapReduce recently. In the end, you have to conclude that you couldn't escape the technical difficulties. The garbage collector came to get you, right? So MPI gives you a different set of complications in that you have to do your memory management and you have to do more message passing than you would do otherwise, right? But at scale, you rarely can completely escape the technical difficulties of distributing things, right? And you didn't really.
Well, so the idea here is that if you're using a UI, because of the complexity of the UI, you will probably not even be able to do, or if you want to do something on this, you have to spend a lot more resources because developing the cost is much higher. It's true that we hit garbage collection problems. And that's a drawback, and that's also one reason why I conclude that the Spark framework is not ready for everybody yet. It's not like easy to use as they claim it is because of this problem. But I can also see that they're working on right now to do the manual memory management for you. So as these tools mature more and more, as we see for example with MapReduce, you don't need to think about it. Or Google Cloud Dataflow, which also, I haven't tried it, so there might be other things, but they also say that, okay, we will do the tuning for you, we will do all these things. So you can use this at the virtual machine was a big overhead, and now it has been optimized so much, and you get it for free. The Java code I wrote in the 90s has become more and more efficient because there's been a lot of work involved into optimizing the virtual machine. And then, again, you have the problem that, yes, true, you can do something more efficient if you use MPI-C. But in order to handle things like load balancing and fault tolerance, you need to spend so much more work that you are very likely to introduce bouncing program, and typically people that just don't do it.
Right, but the thing is, it's the argument of the thesis that somehow this is an argument, like from an algorithmic engineering perspective, that using these modern tools we can accomplish easier things.
Yeah.
However, in the end you did not accomplish it, right? Because your scaling has to stop at some point because you got in trouble with the garbage collector and the graphics library, right? So in the end, this thesis cannot constitute an argument that modern tools are better because you fail at that.
Well, I will never say no one probably able to do something that's complicated, doing this much research into proxies and generalized algorithms and so on, and implement it using MPI. That is fault tolerant, distributable, and so on. Then there's a claim I cannot support by any basis of fact, but
no, I believe that.
Yeah.
I can see that.
And if this was a production service, you could have spent time doing the garbage collection tuning. That would probably solve the garbage collection problem. You could have spent time not using an alpha library for graph and doing the graph computation. It's not that difficult. That cannot be done.
But this is the thing, when you're doing things at scale, right? You're not done until you're done in the end, right? Because at scale, all the problems manifest themselves, right? So you stopped at the one where the garbage collector got in your way. And you hypothesized that you can get a little bit more space by doing better representation Java objects, right? But there's no telling that once you get the garbage collector parameters right, that there won't come the next problem somehow, right? So this is the difficult bit of engineering distributed systems and parallel systems at scale, right? So I really don't think that your argument, that your thesis, brilliant as it is, can support the argument that the modern tools are substantially better than the one we had previously. I mean, I believe that's true, right? It's just not a conclusion I can base from this thesis.
Okay.
Another, right, in this sort of general area versus cloud versus grid computing or standard distributed computing, there must be a lot of data, right, that you have to move to the cloud somehow, and especially in metagenomics. I mean, how would that present a bottleneck in this, or issues in this?
Well, so for example, here,
this cloud computing.
typically the big thing, especially on universities, is not moving data to the cloud because universities have pretty good internet connection. The cloud providers have even better internet connections. I was working on 25 gigabytes of data.
That's not so good.
And I ended up having like several hundred gigabytes shuffling data around. That would be the same if you were a grid engine. So it will take long, it's much longer to run that with even a grid engine than upload the data. So moving the data to the cloud is not a big thing. And storage is also,
I talked to the guys at Metagenomics Lab, and they frequently simply mail a big hard disk. I mean, to
like post.
Yes, post. classic snail mail package with a big hard disk.
Okay.
With everything, because the data is so huge. I mean, you have, and especially in metagenomics, right? You have tens of thousands of genes of.
Yeah, I don't know. I mean, at home when I have a normal core connection, I give out a quarter of terabytes sent with Dropbox. That's not a problem if you several terabytes and only upload it once. If you have to sync it all the time, you might become a problem. Although it once this one, I have not heard anybody saying that that is the prohibiting factor for moving to the cloud.
Okay, so I'm a bit interested in your talk with the garbage collector on technical level also, right? So you never mention it in the thesis, so I just wanted to ask you did change the heap size, right? Because the default is to 1 gigabyte, right? And then you have to go garbage collect.
Yeah, but the Spark framework changes the heap size by default.
Okay,
so
right.
Also so it has some. But at that point, I was sitting with broken fingers and couldn't really do that much. And I thought, okay, I can spend a lot of time getting this to work, or I can say, okay, the point we have now, from an academic point of view of evaluating the theoretical aspect of algorithm, is actually pretty good. And then as well as that, it's not free. So the area where I did the proposal garbage collection, I was paying
So what do you imagine would help? How would you go about choosing the garbage collector?
Okay, so if I would do it, the first thing I would do is to switch to the G1 garbage collector, which seems to have some really good properties. The second thing is I would probably increase the number of threads that I use, because the defaults should apparently be pretty low, so if you increase the number of threads, which means that you might slow down your normal computation, but if you avoid having these long breaks where everything freezes, that would be great. So that was something. If I should be completely honest, with the experience I have right now, I have to do this again, I will probably do a test, or actually a new thing, I'll probably do a test on the Google solution, see how well that works. Because tuning garbage collector, that only complains when you're doing on big data sizes, so it's difficult to have these rapid iterations and solve the problem, is a problem, definitely. So hopefully when these tools mature more, they will be easier to use. But yeah, definitely G1, more threads. I think the G1 takes away a lot of the things by managing the new and old generations, how much space there. So there are few things to optimize. But there's definitely still a lot of things.
Right. Okay, so speaking of Google's framework, so you dismiss it in the thesis, saying that there's a lot of boilerplate in that work because it's in Java 7. But later you mentioned Scala, which runs on the Java 7 engine, or the Java 7 JVM.
Yeah.
So
boilerplate is the code you write, and Scala has a whole bunch of syntactic sugar on top of the JVM, so it combines the same bytecode, but language is actually different. I think the example I have in the thesis shows pretty well that you can do one line in Scala and Spark. You can do the same, that takes 10 lines in Google Data Flow or Java 7. So it comes down to two things. First of all, you use Java 7 where you don't have lambda functions. That will be fixed in Java 8, so that will be better. But it also comes down to have this general do par function that kind of is a catch-all thing. You don't have all these nice, simple, functional programming functions like map and filter and reduce and duplicate and so on. They don't exist. You depend on having only predefined library functions like count element. But if you need to reduce some other way, like you have to write more about that. But that's easier to do than tuning garbage collector, definitely.
Yeah, but this is fine. You also you mentioned in the thesis that Apache Spark is somehow more modern, or somehow is better than traditional MapReduce frameworks. How is that?
So there are several things to that. The most important one is the flexibility of the UI. So MapReduce, you have to fit into this. You take some of the key value pairs, you take some values, you map them into key value pairs, they reduce and group by all the values and so on. And you can now have been some optimizations where you have tried to make or inject a reducer before you do shuffling, because that can optimize stuff somehow. Because you realize that sometimes, for example, you want to do a song, it's not really efficient to shuffle all the values individually and the song afterwards. So you have, and if you, so because you're forced to use these very few, very limited functions, it's difficult to do, or it becomes more difficult to write easy to read programs. You can do it, most things you can do. There's also an issue with if you have iterative programs, because it runs everything to disk, so it becomes a lot slower.
Yeah, but so my understanding of Apache Spark is that it's still essentially a MapReduce framework. It gives you a little more flexibility, but the big difference is that it's lazy.
That is what?
That it's lazy. That it's mental, that it doesn't necessarily recompute everything.
Yeah.
Right. So to me, Apache Spark is still a MapReduce framework, but it's with a lazy computation demand.
Well, I would say, how would you define a MapReduce framework?
Very nice. So I would say it's a framework that on some level requires me to first local map function and then eventually reduce those.
Yeah. I think we agree on that. On that point, Spark is not a MapReduce framework, because you don't have to invoke maps, you don't have to invoke. You have these filter functions, which essentially is not a map function. You might be able to implement it, but you are able to take algorithms and move from MapReduce to Spark. You can probably move one-to-one, but you have more flexibility, and you can do joins and so on, which are like default in MapReduce. So the programming model is more flexible. It's not like, oh, this brave new thing that's it's not as new as MapReduce was when that first came out.
Yeah, cool. Okay. So the reason I asked about that is, and maybe we can get into more technical bits, to me the big thing about Apache Spark is that it is lazy. It's lazy. That nothing is computed until it's required for the final conditions, right? And usually, especially in functional programming, that has ramifications for space consumption, the space complexity of my programs. So in your thesis, you say, can I tell you this? Where is it? On page, do you have the thesis slide so we can get it up?
Yeah.
On page 80? No, not page 80. In the beginning of page, you have this, you make this, you put it on a little framework for evaluating complexity of a Spark program.
Yeah.
And this is on section, little boxes on pages 15 and 16. And in definition 3.1, the most important complexity measure for anything else for Apache Spark. So I would say that the space complexity here is missing.
So you're talking memory consumption during.
Right, because I mean I can write silly MapReduce. I mean if I write a stupid MapReduce program where my reduce function doesn't really reduce stuff, but it keeps a big table thing or whatever, then if I'm using say linear space at each node in my sort of little computation, then I'll get something that scales in space linear. That would be terrible. Right?
You do have a pointer, but usually the way my impression is that the shuffle size is typically very closer to how much you use locally. You can of course use a lot of RAM locally, but that will either be temporary in each map task, which will quickly be able to be reclaimed. But if you do stuff where you have a whole offset, you can the shuffle size is that will usually be related to shuffle size, which is not the network. One thing. Secondly, if you have the data generated, so that's partly covered by the runtime. And thirdly, if you run with many gigabytes RAM and have disks to store into, I'm not saying it doesn't matter, but I'm saying that that's typically much faster than, say, shuffling over the whole network.
But you got in trouble with garbage collection. That makes me think space.
Yeah, but I mean, I got trouble with garbage collection because I have a lot of small objects. I mean,
sorry.
Because I have a lot of small objects. I didn't get in trouble with garbage collection because I ran out of RAM. Also, only using half of RAM.
Do you know that?
Yeah, because you can see the plots.
Right, but the garbage collector will run when the garbage collector sort of decides that it seems to be running low on RAM, right?
Yeah.
So it seems that the more space your program consumes, the more pressure there will be on the garbage collector. So if the space complexity is bad but manageable, then you can get in trouble with the garbage collector, right? Whereas if the space complexity is good, then maybe you come in less trouble with the garbage collector. So maybe what I'm asking for is, can you make like a cohesive, compelling argument that no, you are not consuming too much space in your implementation of the cluster?
Well, I think the biggest problem with space consumption is the object overhead.
Is what, sir?
It's the object overhead.
What kind of stuff do you actually create in your algorithm? I mean, what objects are you building?
So essentially I'm the place where it an object for each non-zero value in all the k profiles. And the big problem here is that that's a hill of a lot of objects. It's not because that if you store these as a array, it would be that.
Right, and okay, so you're doing this, I mean, for the entire vector of k values of
the issue is
to the k length, or?
I need to shuffle around so I switch the protocol.
Yes.
And the only way to do that in Spark, and I also mentioned in the thesis, that there's a problem that we cannot do it more efficiently with arrays because the API of Spark doesn't allow that. So internally, Spark typically uses array for an internal implementation, but only if it can infer that. So if you, for example, use an object as, if you have a key value pair with primitives, it will use arrays internally. But as soon as you get an object, which I have as one of the value, you start to begin having, it cannot yet optimize that. Maybe in the future, perhaps not.
Maybe it's sort of the issue that arrays are not that easy to distribute.
I mean, if you're sending one array to one place, it's not.
But I mean, big arrays. I want to chop them up. That's
Well, array is probably the easiest thing. I mean, it's just, and in the representation job, it's just a piece of data. All the memory you use is on data, unless you use you include all the 0 elements. So of course, if you need to flip them over and pick elements from each array around, then you're right. But if you're sending one array from one machine to another, I don't see a problem.
No, but I'm thinking sort of, this MapReduce framework is not really clear how to. I mean, it's non-trivial to do that. It's non-trivial to do that in a MapReduce setting, at least to work on arrays that don't fit and don't partition, don't fit on a single machine, right? So you want to split them out and computation on the lower parts of the arrays, then how do you do that in MapReduce?
Yeah, that might be true, but if you do a quick assessment, if you have like a primitive array of integers, and you have your full integer max, then you're using a few gigabytes for that array, so very easy to figure.
Right.
So it's true if you start having arrays of strings, but then you can load objects, and so on. But yeah, it might be a problem. In all the things, applications I've seen, I've not seen that large arrays, because when you get to that size, you don't stop. You usually don't think of it as an array, you think of it as a collection somehow. And then you have each element in the array anyway. For example, you don't have an array for web pages. You have a collection of web pages, and then the framework chop it up and so on. But you are right, if you have insanely large arrays, especially if they are longer than most nations support, like integer max, then yeah, there could be a problem. But I don't think that's the problem in this case.
Wow. So do you have any more questions?
I can keep going.
On which parts?
So
Some new stuff other than Spark, and we should get around some of these.
yeah, sure. Okay, so it's like a conceptual question for your generalization of the Disco algorithm. Could you argue why in your setting it's, so Disco is probabilistic in that we add these random variables to sort of get a sample of things, and then we know that we still get the most, somehow the most important correlations in the end, and this is good enough for Twit, right? Because this is good. So why is it good enough for biogeneticists? Wouldn't they care deeply that even the pairs with low correlation still has the correct correlation?
Well, yeah, you're right. And that's also a reason why we have the cutoff value pretty low and lambda pretty high, so we have very few false and negatives. So that's definitely an issue. On the other hand, the way that they currently use the common software where you do this alignment, and the alignment is not really based on any sound knowledge. The knowledge is just people trying to tweak different parameters. And for example, we saw here, in the report, we see that CDHEN has a lot lower quality of the clustering because it uses another definition of an identity. So the fact that we miss less than 1 per 1,000 pairs is neglectable compared to the differences you have by tuning the parameters of this alignment algorithm, which different tunes do differently. or for example this 95% audio. These are the same, these are not the same. And as far as I know, and I've talked many about this, is that there's no really good reason for this, just people start using that. My personal belief is that people used to take 95% when they're doing probabilities, and say you have to be statistically good, then we're 100%, and that's the same here. And to me that seems pretty weird. And I've also seen charts that show that the same gene from the same bacteria is mutating a lot of ways. Those ranges from like 60 up to 100%. So you can find things, and we know these are the same bacteria that mutate, that's only 60% similar when we line. So I will say, yeah, it's right, it's not perfect. And the scalability is not perfect either, because the way we add more data is kind of on the wrong dimension, so we add more rows in the matrix, and it performs well if you add more columns. So yeah, it's not the perfect fit, it might be better or not. But I would say, when it comes to false negatives, it's a much bigger problem that the definition of what is the same gene is, to me, as a computer science, is baffling.
Yes.
That we're doing that much science on something that is so little understood, and the alignment that we've done optimized for the identity. So you might say, argue that this is a better alignment, but then you get a lower percentage. But you still use 95%, because that's the right thing to do.
Right.
So I would say that's a much bigger problem.
Okay, but if you go to the sort of thing, if you go to page 52 in your thesis, 52 in my PDF anyway. I won't have 52 in the
Let's try to see 52 here. This one?
Yes, yes, no, it's page 40, sorry.
Page 40?
Numbering my PDF, yeah, sorry. Yeah, so this is where you define your random adders. You put them down in 6.2 and 6.3. Could you say a little bit about the specific choice of Bernoulli variables and random variables and significance of the sign here?
Okay, so the idea is that I try to be as close to the original algorithm as possible. So the Bernoulli variable is just 1 or 0 probability of so we want to say if it's something that has have something that has the expected value of A. And the expected value of this Bernoulli is the probability of negative 1, or the probability time. Then you add the sign to get the same sign.
Right, but there are lots of distributions that will give you an expected value of A, right? So why this one specifically? I mean, I could just a constant one.
The important thing is that it is often 0. Well, it's because of the low values, it is often 0. If you have another distribution that wasn't 0 often, we wouldn't get the efficiency of getting fewer keys. You might be able to find another one that has even more zeros than this Bernoulli distribution. And that will, in that case, could be a better solution. But on the other hand, you might need to increase the lambda more in order to get a better approximation.
So in the written disco paper, they have a very long and cumbersome calculation of why the choice of random variable will keep them within a certain error bound, right?
Yeah.
So in your case?
So in my case,
can you argue that I mean, so you compared to the exact solution that you obviously don't want to compute because it takes too long, right? Then clearly this will introduce errors because you have an error, you have a random variable, right? But can we quantify this error?
Well, so I've done the proof around the bounds of error.
Yeah, so I wanted to sort of say some more about that.
Okay, yeah. So the idea is that by using this Bernoulli thing, we can use the Markov. I can't remember the name of it actually. We have this inequality that because the variable is I think it's between 1 and 0. I can't remember the exact thing. We use this rule. Well, they also use this paper for what are the bounds. We can use that on the Bernoulli variable. I'm not sure you'll be able to use that on any other distribution you pick. Probably not. We definitely have some issues with negative values that we cannot use for. So, do you want me to go through the proof again?
No, maybe I was because I was confused by this because it wasn't clear to me. And this is like opening the question, right? Whether it's obvious or not that you can generalize Cisco to having real value mixed components instead of just the binary ones they had originally. I can't determine if it is like, obviously just put it in, you do the proofs again, you get the same thing, or if there was some key that I missed in your tools?
I mean, the proof is pretty simple once you have defined certain.
Yeah, but it looked to me to be kind of sort of the same as in this table on like a quick.
Yeah, so the idea, there are two things that are kind of the contribution to new things. First of all is to figure out how do we deal with that with another starting number, or and alpha starting number, because they don't, you can discuss them.
Right.
They mix it a little bit because they might be depending on the tune parameter, they might get something that's above or the length. And then we say that just throw aside and say, okay, the reducer should take care of that, and the good implementation do that. That's kind of what they say. So we don't really deal with that in more detail. So the idea of defining this thing instead helps us do that. And then the proof, the new thing in our proof, which was just a copy paste, is that we isolate these two regions. So we isolate these fixed parts which we always, there's no will be emitted, and always has the same value, and these parts here which are actually random. So that separation and showing that we can still use the same proof if we separate those two out, that is the contribution part.
Right.
I think we're running out of time, so we should say thank you, right?
Yeah, thank you.
Yeah. So,
Tillykke, og så er der et lille glas herinde, hvis vi må være herinde.
Ja, det må du godt, tror jeg. Do you want some champagne?
Yeah, champagne.
Maybe just a little. I have to get back to work.
Yeah. We have water too.